So, today we'll be discussing the week 12 of the deep learning course. This is the last week of the course, and I think you'll have your exams after this. And what was covered in this week was denoising, image denoising, variational autoencoders, and some introduction to GANs, generative adversarial networks. So if you have any doubt regarding the content or anything that we discussed in the previous weeks, then you may ask those doubts. You can just interrupt me in between or post it on the chat. Okay. So let's discuss some problems from week 12. The first question is the dice coefficient is computed as. So there are four options, which are four formulas, and we are asked which is the correct formula for dice coefficient. Okay. So if you recall from the first lecture of this week, the dice coefficient was defined as 2 times number of elements in A intersection B divided by number of elements in A plus number of elements in B, where this A and B are what? So basically this dice coefficient is used to evaluate segmentation output with respect to ground truth. So if you have two images, maybe I'll just take some image image segmentation. Okay, so this is some image. So if you see these two images, this is an image where there is a lady standing and the lady has been segmented out, while the model's prediction, so this is the ground truth which we want ideally. So someone has probably manually traced out or segmented the person, while the prediction is given by some model. And if you look at the model's prediction, it doesn't perform as good as the ground truth, but it does well in the sense that it is near the image. It is not an arbitrary position like this one. It's close to the person, so it's okay, not worse. It could have been worse, but it could be better also. Like the right hand or one of the hands of the person is not captured, the face is not entirely captured, some extra region of the grass and in the background is captured, so those could have been avoided. So how is this formula capturing the evaluation of the segmentation? Let's say A is the set of points, set of pixels which are predicted as, so basically these regions are predicted as 0 each pixel, and each pixel which belongs to the person will have 1. So A is the set of positions where in the ground truth set of pixels in ground truth where where you have 1. Okay, let's say f of xy equal to 1. Set of pixels means the positions x comma y. Okay, set of pixels x, y in ground truth where f of xy equal to 1. F of xy is your model, and these, so I should not say f of xy, so because ground truth is not coming from your model, let me just say gt of xy. Gt is ground truth, and b is the set of pixels x comma y in prediction where fx comma y is equal to 1. Okay, so those pixels where the model has predicted that the person is there, that is this region, all these pixels. So A intersection B would mean what? A intersection B would be intersection of this region and this region. So that would be in this region, right? So the red region is A intersection B. So we want to count the number of pixels, that is this A intersection B number of pixels, twice that, divided by the number of pixels the whole region in ground truth, that is the cardinality of the set A, and the number of pixels in the predicted region, which is predicted as 1, that is the cardinality of the set B. So if the ground truth, if the prediction was same as the ground truth, what would happen? A intersection B would be same as A, right? If prediction is same as ground truth, then A intersection B, basically A intersection B is equal to A. So number of elements in A intersection B is equal to number of elements in A. So the die score will be what? 2 times A upon, so basically when prediction is same as ground truth means A is also equal to B. So number of 2A upon A plus A is equal to 1. So when the dice coefficient is 1, you have perfect segmentation. So if this region was segmented, that means A intersection B will be equal to 0. So the die score will be 0. But what the question is asking is the same formula in terms of true positive, true negative, false positive, false negative. So how can we convert this formula into in terms of these values? So if you see, A intersection B is what? All those pixels where the ground truth is also 1 and prediction is also 1. Okay, that will be true positive, right? So A intersection B is equal to true positive. And A is all those pixels where ground truth is 1. So ground truth is 1 at true positives and false negatives. Okay. And B is the set of pixels where prediction is 1. So B is 1 at true positives and false positives. So then what is the dice coefficient? That is 2 times this upon A plus B, that is 2 times true positive plus false negative plus false positive. Okay, so which option is that? It is a C option. Okay, was this part clear? Okay, I hope this part was clear, how we computed what is true positive, what is false negative, what is false positive.
Yes, it is clear.
Okay, thanks. So let's look at the next question. What is the relation between Dice coefficient and Jacquard coefficient? That is intersection over union. So just now we discussed Dice coefficient. The Jacquard coefficient, I think it was not discussed in the lectures, but we had discussed it in the previous week's problem solving session. This is basically uh, A intersection B upon A union B. This is the Jacquard index or Jacquard coefficient. So they are asking what is the relationship between these two. So how can we find that out? The Dice coefficient is greater than Jacquard coefficient. So Dice coefficient is 2 times A intersection B upon, so let's suppose that let Dice upon Jacquard equal to K. Okay, so if I divide Dice divided by Jacquard, what will I get? 2 A intersection B upon A plus B. This whole thing is divided by A intersection B upon A union B is equal to K. So this is equal to A union B twice this divided by plus B, right? Now maybe I can write uh, this in terms of okay, A union B is what? It is the set of all pixels which are predicted as ground 1 by ground truth as well as the prediction. So it will be true positive plus false positive plus true negative plus false negative. Oh, sorry, true negative will not be there. False negative. So in true positive, both are 1. Both ground truth and prediction pixels are 1. In false positive, prediction is 1. In false negative, ground truth is 1. Okay, so that will be A union B. So what you have is this is equal to upon this is what so A just now we saw is true positive plus false negative. And this is true positive plus false positive. This is equal to K. Then we can write 1 by K is equal to 2 times this plus so what does this mean? I can write this as TP plus Fn plus Fp plus this is not giving us that much information. What else can be done? Okay, this can be written as right. So this is equal to 1 minus Fn plus Fp upon, okay. Now this term is clearly positive because this is Fn plus Fp and this is Tp plus Fp plus Fn. So this term will be greater than the denominator will be greater than the numerator. So this will be a small fraction. And so what you get is 1 by k is less than equal to 1. Okay. That means dice Jacquard by dice is less than equal to 1. So Jacquard is less than equal to dice. So that is C. When there is no false negative and no false positive, this term will be 0. This term is 0 means k is equal to 1. K is equal to 1 means both Jacquard and dice are equal and are equal to 1. Okay. So from this I actually came here. We can remove this. Okay, so we just used the ratio of the dice and Jacquard coefficient to find out if there is some relation between these two, and we wrote these coefficients in terms of the confusion matrix values: true positive, false positive, false negative. Was it clear? Okay, so both of these can in some way be used for evaluating segmentation. Okay, this question is asking which of the following is not true for training denoising autoencoder. So the purpose of denoising autoencoder is if you have some noisy image, if some image is there and there is some noise in it, you want to give it to your denoising autoencoder and gives out a clean image. It removes the noise, denoises the image. So option A is a clean image X is corrupted with additive noise, and you get X tilde is equal to X plus epsilon before feeding to the network. So they are asking which of the following is not true when you're training a denoising autoencoder. So when you're training a denoising autoencoder, you want to create training data. So how do you create training data? You need some images which have noise and the clean versions of the same image. So when you're training, you want to uh, train a model in this in such it's a supervised learning task. So you want the label. Your label is basically a clean image, and your input is a noisy image. So how do you create this data set? You collect a bunch of clean images, and this is X. Then you create a set X tilde. Like this image X, you create X tilde by adding some noise. This noise may be from some version, something like that. Okay. So this is the noisy image, and that you will give you to your model when you are training, and you want your model to reconstruct the clean image. Option B is saying the network is trained by minimizing the mean squared error. So you would want to minimize the mean squared error, right, between X. This is what you would want to minimize. Between your noisy image and your clean image. So both option A and B are true. C option is asking the mean squared error is computed between the network output, which is some X hat, and noisy image, X bar, X tilde. So what did you do? Okay, this what I wrote here is incorrect actually. From your model you will get X tilde and compute it with respect to the clean image. So you have your model. Okay, first you have some clean image. You create X bar, which is equal to X plus this. This is your noisy image. This is clean image. Now you have some model. Let's say F is your denoising autoencoder with some parameters theta. Then you give this noisy image to it, and you get a prediction, which is x hat. So now you want to minimize the error that will be between x hat and x, right? The mean squared error that you compute will be between x hat and x. You want this error to be minimized. Okay. So but the option C was saying that the squared error is computed between x hat and noisy image. So if you were to do this, your model will again learn to predict noisy image itself. But what you want is the model to learn to predict the clean version of the image. So the option C is incorrect. So this is the option which is not true. Is it clear? So the question was asking about training of a denoising autoencoder, which is what you will use for image denoising. It will be a convolutional autoencoder kind of thing. And we also saw in the convolutional autoencoders you have some skip connections. Okay, there is no doubt in this. I'll go to the next question. So in this question they are asking, for an autoencoder, suppose we give an input signal x and a reconstructed signal y. Which one of the following objective functions can be minimized to train the parameters of the autoencoder using gradient descent optimizer? So we have a bunch of candidate sort of loss functions, and we are asked which can be used to minimize uh, to train the autoencoder such that we are able to reconstruct y from x. We are able to reconstruct back the input signal x basically. Y is the output of the model. So when x is very close to y, we want our loss xy to be close to 0, right? So we can just check for which lx comma x is 0. So exponential x comma x will be e power minus 0 is equal to 1. Okay. Here they are saying x minus y is 0. This will be equal to minus log 0, which is basically infinity. In this option, lx comma x will be equal to e power 0, which is 1, while this it will be x squared. So none of the options are actually going to 0, but still we may be able to use this if whatever value that you are getting, let's say lx comma x is equal to some k. If I were to use uh, give some y which is sort of not very close to x, then lx comma y should be greater than k. Okay. So this D option we can straight away discard because it will not hold. If I use x with bigger values, if x is very high, then lx comma x will be very high. Okay, if x is some high value and y is, okay, this would have been 2x square, right? If x is very high value and y is 0, then I'll get x square, which is a very high value. While if x is small and y is also small and they are both same, then I'll get a very small value. So this is not a very good loss. And another thing is, when x minus y, this value, if x minus y, this is decreasing, then my L should also decrease. Okay, so that is something we can check. So in the A option, what we have is A is exponential of minus z, let's say x minus y is equal to z. Then e power minus z is something like this, right? So if z is small, then my value is high, and if z is big, then my value is low. So this I don't want to use. So I've discarded A and D. If I look at B, then I have minus log z. So if I look at the derivative of this, it was d by dz of minus log z. This is equal to minus 1 by z, right? So when z is increasing, my function is decreasing. Okay, this is less than 0. So my function is decreasing. What I want is an increasing function. When z increases, this is my z, and z is increasing, L should increase. And the other way also. So if I look at C, is exponential of z, then this is an increasing function. Exponential of z is like this. If z increases, my loss also increases. So C is the correct answer. So what we had to check was, when the distance between my input signal and the reconstructed signal is increasing, my loss function should also increase. And when it is decreasing, loss function should decrease. So basically I wanted a monotonically increasing function in terms of this mod x minus y. Okay, any doubts in this? Okay. Okay, so this question is asking the KL divergence between two discrete distributions P and Q is given as which of these following? So here the KL divergence is not really a metric, in the sense it is not symmetric. KL QP is not equal to KL PQ. Okay, and we are using this to sort of, it's a sort of measure of the relative similarities in some sense of two distributions P and Q. So the formula is actually straightforward. It is the A option. You just had to know which one it is. So if it was KL PQ, it would have been summation x P of x log Qx by Px. Sorry, log P of x by Qx. Okay, so this option is actually KLPQ. Okay, so any doubts in this part? Well, just the formula of the KL divergence. Which one is correct? It's the first option. So I'll go to the next question. What can be the minimum value of KL divergence metric? So what you had was summation KL QP is QX log QX by PX. So what is the minimum value that this can have? So can it be 0? It can be 0 if Q of x is equal to P of x, right? If Q of x is equal to P of x, then what you will have is summation x Q of x into log 1, and log 1 is equal to 0, so this will be 0. Okay. Now what is asked is what is the maximum value? This is the minimum value. And this may not be the minimum value. Can it go negative? No, I think this is the minimum value. The other thing is the maximum value can be if P of x is 0 for some x, right? So let's say Q of x is some normal distribution between 0 to a normal distribution with 0 mean and some sigma, and P of x is uniform minus 1 to 1. So if I compute the KL divergence, then what I'll have is summation minus integral over minus equal to infinity my Q of x into log qx by px dx. And this you can like split into minus infinity to minus 1 qx log qx upon px will be here 0, plus you will have some minus 1 to 1 thing, and again 1 to infinity, where again you will have qx log qx by 0 dx. So this will be log infinity, which means this term will be infinity and this term will also be infinity. So the maximum value that KL divergence can have is, let's see, yeah, okay. So what we did was we took two distributions which are not same and we saw what value we are getting, and it turned out to be infinity. So that we can say it from looking at the formula also, like P may not have non-zero probabilities at all the places where Q has a non-zero probability. So at all those places where P of x is 0, this log term will become infinity. Okay. So let's look at the next question. So this question they are asking KL divergence between two distributions is the same thing, just the formulas are different this time. So which one is it? So KLQP, we have seen it is summation x q of x log. Let me connect my charger. Yeah, this is log qx by px. So we can say this is the expected value, then you consider this as a random variable, some x. X is basically a random variable, some function of your f of x. So it is basically summation x qx f of x, which is basically expected value of when x you are sampling from your qx f of x, and this f of x is basically log qx by px, which is log qx minus log px. So that is the D option, right? So you're sampling from the Q distribution and computing the expected value of this term with respect to the Q distribution. Okay, so just that same formula is rewritten in a different way. Okay, I think this was quite straightforward. So there are two statements and they're asking which are true and which is false. So first statement is the reparameterization trick used in variational autoencoder for backpropagating through a random node. Okay, reparameterization trick is used in VAE for backpropagating through a random node. So in VAE, you have your decoder. Decoder will give some for some x. It will give mu x and sigma x. And this is your encoder, sorry. This is your encoder. And the decoder, for decoder you sample from this a z. You sample z from normal mu x comma sigma x and give the z to the decoder and gives you some y. Okay. Now what is the reparameterization trick? That is when you have your when you are doing backpropagation, the z is a random variable which you are computing from your mu x and sigma x. Okay. So let's bring this down a bit. So here let's say there is some f of z. So this part you can evaluate as df by dz. We use a different pen. Okay. Now to do this, you can't really do dz by d mu because z is not some function of your mu, right? Z you are sampling from a distribution which is parameterized by mu and sigma. Z is a random variable. So the reparameterization trick, what it does is you make your z not a random variable by introducing another random variable epsilon. So this is computed basically z is equal to mu x plus sigma x times epsilon, and this epsilon is from normal standard normal distribution. So now you can compute the gradient of this del z by del nu x is basically 1 and del z by del sigma x, this will be for some ith component, it will be epsilon I. Okay. The z ith component like that. because mu, sigma, these are all vectors. Z is a vector, epsilon is a vector. So this is basically the reparameterization trick. So the reparameterization trick is used in VAE for backpropagating through a random node. So that is what we did just now. So statement 1 is true. The reparameterization trick does not work with discrete latent variables. So what does that mean? For a random variable we were able to do it. But what if instead of a random variable z was a discrete variable? That means z is some sine of mu x plus sigma x. Let's say. So now z becomes a discrete random variable. So this will only take values in -1 and 1. Okay. So because it is not continuous, because this is not a continuous function, you can't, the derivative is not defined. Or the derivative will be 0 at most of the places. So there will be no backpropagation. The sine of x is something like this, right? Plus 1 minus 1. So at all these places it is 0. Here there is a jump, it is discontinuous. And here all the derivative is 0. So this reparameterization is not really helping in backpropagating through a discrete latent variable. Okay. So it does not work. So that is also true. So both the statements are true. So any doubts in this? Okay. Okay, so in this question they are asking, suppose we have a trained variational autoencoder on faces with 4D latent code, and after convergence the mean vector and standard deviation vector is given by these two values. That is, in variational autoencoder you assume a prior distribution on your latent space. Okay, that prior distribution is that it is from Pz is from some normal mu z sigma zi. I should not write z here. Maybe I can. So this is the prior distribution that you assume. Z is the latent variable. So this mu and sigma is sort of computed as this thing. So now they're asking now in the evaluation phase, that is now you have given, now you have trained your model and it has converged to this sum mu and sigma. Now in the evaluation phase, which of the following latent code is most probable to be encountered when we pass this new face image? So when you are passing a new face image and your latent space distribution is this, that is a normal distribution, and they are asking which is the latent code which is most probable. So most probable code will be close to the mean for a normal distribution, right? Most probable latent code is close to the mean mu. Mu is this 2.1 minus 1.9, 3.8.29. So you can just see which option is the closest. So you have 1, 3.9, 2.9, 3.2. There is 2 minus 1.92, 3.8. So what the other thing, the mean was this, right? 3.8, 0.9. So these two are quite close. Here there is, this is positive, this is negative, and this is negative, this is positive. Here also it is sort of different. So this you can see is the closest. So B will be the most probable to be encountered when we pass the new face image. Okay. Any doubts on this? Why is it called latent? It is called latent because uh, sort of what you are doing is you have some set of input data, and when you encode it, you're encoding it into some distributions which are independent of each other. Here this mu vector and mu, like for given x you get mu x and sigma x vector. Okay, so each component of z that you sample is coming from this normal mu xi comma sigma xi. So we say they are like some hidden features of the your image, which is enough to sort of describe the image. So latent in some form means it is hidden. It's not apparent in the image or your input data directly, and the model learns it if it is able to give good sort of minimize the loss quite well. It is, if it is able to converge, that means it has somehow identified some latent variables from your data. Okay. So overall the z is coming from normal mu x comma sigma x into y. So this is the mini by stochastic gradient descent training algorithm of GANs, and this algorithm was shown in the lecture also, I think. Okay. And this is the paper in which it was proposed, and the question is, which of the following statement is true for the GAN training algorithm? Option A is the parameters of discriminator D are optimized first. The parameters of generator G are optimized first. Alternatively, both D and G are parameterized. Uh, Alternately, both D and G parameters are optimized. None of the above. So in GANs, what you have is you sample a random variable from some normal distribution, and the Z you feed it to your generator G. It produces some X, and your discriminator sort of takes this X as input. Okay, discriminator is something like this, and it sort of predicts a value between 0 1. 1 means it is a real image, 0 means it is a fake image. Okay. So they are asking what happens in the GAN training algorithm. Is the discriminator parameters optimized first? Is the generator parameters optimized first? Or alternatively, both are like sort of optimized. So you optimize some parameters of this, then this, then this. Alternatively, you keep doing that. Is that how you do? So if you look at the algorithm, like for the training iterations, this is the first for loop. Inside that, there is one for loop for k steps. So k is a hyperparameter, and k they are setting as to 1. So basically this for loop is not there. There's only one step. So what you are doing is you sample a mini batch of m noise samples. So from your normal distribution, you sample some m points, and from your training data, you collect some m examples. Okay. Training data you assume is coming from some p data x. And what you want to do is you want your model, whatever you are creating, the model is generating the samples x. So the model distribution of x, you want it to be similar to the data distribution of x. You want to sample images which are similar as what is there in your data. So you sample some, and this p data is unknown to us. Okay, p data is unknown. From nature we have just collected some data. So in the first step you are updating the discriminator by ascending its stochastic gradient descent. So the discriminator will want to predict x as real. Discriminator wants to predict x as real and z as unreal, z as fake. Okay, that is the job of discriminator. While the generator, what it wants to do is it wants to create an x from z such that it is able to fool the discriminator. So that means if it wants to minimize this, it will want to predict it will want to make this d as 1. That is, it predicts discriminator should predict the generated image as 1. So in this algorithm we can see here you are updating the discriminator parameter. The gradient is with respect to this theta d, that is the discriminator parameters. This is theta d, and this g will have theta g. Sorry, what happened? This will have theta d, theta g. So this gradient is with respect to the generator parameters. So alternatively, you are updating discriminator generator and you keep doing it in as many as a number of training iterations go. So the correct option is C, alternate between D and G. So what will happen if you just keep doing updating the discriminator parameters? That would mean like the discriminator, you will make it very good at identifying what is the real image, and because you are not updating the G parameters, the G will keep producing fake images which is not really close to your P data. Same thing will happen if you optimize G first. The generator, because you are not really training the discriminator, the discriminator will be very bad. It won't be able to sort of identify what is the fake image. Even if the generator is bad, the discriminator will still predict those as fake like real images if you don't optimize the discriminator. So you have to alternate between both D and G. Okay, any doubts in this? So the algorithm was given, so we can straight away sort of figure out what is happening in it. Okay, this is kind of the last question. Okay, so we are on to match left side column with the right side column. So there is GAN here and variation autoencoder. So there are two options, you can see 1 and 3, which has a discriminator and generator. So one of them you have to match with GAN, and there is these two options 2 and 4, which has scale divergence between two distributions, that we have to match with the variation autoencoder. So let's look at the GAN one first, 1 and 3. They are asking this saturates when, probably the training, when does it saturate? So dgz equal to 0 means the model predicts all the images. Like discriminator has become very good at predicting that the images are generated by a generator, they are not real. That means D is doing a good job, but G is not really doing a good job because G is not able to fool the discriminator. So this is not ideally when the model should saturate. The model should saturate when the discriminator is not able to figure out when when the image is from a generator or when it is a real image. So that means it should be this, right? There is a half chance that it is a real image and half chance that it is from a generator. That is what the discriminator feels. That means the generator has become really good. So GAN we will match with 1. And for variation autoencoder, you want to minimize PZ, QZ or QZ PZ. So in the formula it comes out to be this. But how do we justify that? So what we start with is we want to minimize like this P Z given X is something that we don't know actually, and we want to minimize this thing. So how it comes out to be, if you have seen the lectures, this gets split into a reconstruction loss plus maximizing the KL divergence, minimizing the KL, like you want to minimize this reconstruction loss and this KL divergence. But why not this? That I'm not really sure. You have any guesses? So the right answer is this. GAN is 1 and VA is 4. Maybe I'll try to post a detailed solution of this in the discussion forum. Okay, others are left, I think. Okay, one person has joined. Do you have any doubts that you want to ask? Okay, since others are not there, I'll end the session. And yeah, that's it. That was the last question.